about the disc method and the washer method, and now we're going to learn something called the shell method. And what the shell method does is it literally makes a bunch of shells that it stacks inside of this. They're kind of like those Russian nesting dolls where you take off the head and there's another one in there and there's another one and there's another one and there's another one. So that's what we're doing is we are making infinite number of cylindrical shells, and we are creating this figure with those shells. So what we're going to do is we are going to create a rectangle that is parallel to the axis of rotation. And so we have this axis of rotation right there. And so we are going to make a rectangle parallel to that. Now this distance here is the width of that rectangle. So I'll put that on there. That's the width of the rectangle. This distance here is the height of that rectangle. Now the last thing that you need when we're trying to find the volume of this is, well, that's the area of that rectangle. But what we're doing is we're taking that rectangle and we are rotating it around the y-axis. And so that rectangle really, it gets rotated all the way around and it makes a perfect cylinder. I'm not sure how well I can make it. It's gonna make a perfect cylinder with this width. So the width is right here, and we've got this perfect cylinder. And what we're going to do is we're going to take infinite number of these little cylinders and we're going to stack them inside each other. And then we're going to add all of those volumes up. So how do I find the volume of that cylinder? Well, let's say we have a can. And around the outside of this can, there's this thing called a label. My husband, he's going to be really mad at me for peeling this label off. Campbell's doesn't want you to be able to peel labels off, apparently. Okay, let's pretend like this was a perfect peel. In my head, this was a great idea to help you visualize what we're doing here. It's not working out. Maybe I should have ripped it off beforehand. Maybe I should have used a piece of paper. Okay, so we have this, and around it, it was a shell. Okay, how do I find the volume of this piece of paper? How do I find the volume of this shell? Because it's hollow. Well, if I can find the surface area and multiply it by the width, that's going to give me the volume of this shell. So what does that look like mathematically? Well, I need to find the surface area of the shell. And when I find the surface area of the shell, I'm going to do height times the circumference. What's the circumference of the circle? It's 2 pi r. So 2 pi r times the height gives me the circumference, or it gives me the surface area of the shell. That doesn't give me volume yet. How can I use the surface area to find the volume? Well, if I know the surface area of this label, I can multiply it by the width. So we're going to multiply this by the width. We need to get all that information from this so that we can make shells and put them into here. And then we're going to add all of those up, which is the calculus piece of it. We're going to take infinite number of these shells and we're going to stack them inside of each other until we get a full volume. Well, we're going to do 2 pi. We're going to integrate from A to B. In this case, it would probably be from 0 to whatever this is. Okay? R of x times h of x times d of x, where this is the radius, this is the height, and that's the width. So the is always going to be d of x. This formula is going to work every single time you do a vertical rotation. Remember, you're going to make your rectangles parallel to the axis of rotation. So as you would guess, if we were to do a horizontal rotation, if we would have rotated this way instead, we would do exactly this, but we would change this to a y, and that to a y, and this to a y. So now that we've built this and we know where these shells are coming from, let's do an example. So in this example, we are going to find the solid of revolution formed by revolving the region bounded by y equals x minus x cubed in the x-axis. So this area here, keeping in mind that we're only using 0 to 1 about the y-axis. So we are going to revolve it this way. So when you draw this as a 3D region, this is going to curve around. There's going to be this hollowed out center, and then the rest of it's going to be kind of like a rounded volcano, I guess, with that hollowed out center. So the first thing to keep in mind, whenever we're using the shell method, we are going to draw rectangles parallel to the axis of rotation. So here's our axis of rotation. So the rectangle that I'm going to draw is going to be parallel to that. So I'm going to have a rectangle like this. Now the width of the rectangle is always dx. The height of the rectangle in this case is going to be the equation y equals x minus x cubed. That is the height of this rectangle from the x-axis up to there. So our height, h of x, is x minus x cubed. The last thing that we need is we need the radius, because what we're doing is we're taking this rectangle, we're spinning it around the y-axis, and we are making cylindrical shells. So we are making a cylinder here, and the radius is going to be from here to there. And that distance, we call it x. That's a distance of x. And that distance is going to change dependent on where we cut those rectangles. We are going to cut infinite number of rectangles so that we can actually fill this entire solid, and we're going to make all those shells that are then going to pop down and create this 3D region. So the formula for finding the volume of one of those shells is 2 pi r times h times the width. So if we're trying to do, so that's the volume of one shell. If we are trying to figure out what the volume of this entire 3D figure is going to be, we need to do a sum of all of the shells that we can possibly make. And essentially, we want the width to be approaching 0. We want that width of each shell to be nothing. So in order to do that using calculus, we're going to say that the volume is 2 pi, and we are going to integrate from a to b of r of x times h of x times dx. That's going to be the radius times the height times the width. So our radius we figured out is x, so we have 2 pi x. The height is the equation x minus x cubed, and then the width is dx. Now we need to figure out what is our upper and what is our lower bounds. So the lower bound is going to be 0, and then we're going to integrate up to 1. So 0 to 1. Of course, we can integrate this by hand, or we could use our technology. For me, because I have technology at my fingertips, because it's a definite integral, that's what I'm going to do. I'm going to use my technology.
Probably noticed already, Desmos is my favorite way to do calculations. And so you also probably have noticed I'm not very good at technology and the recording the screen thing. So here we go. So I'm going to click on functions, and I'm going to go into miscellaneous, and I'm going to click the integral symbol. in this problem, we were trying to solve from 0 to 1 of x times x minus x cubed dx. What? Oh, I put the dx in the wrong spot. See, guys, I'm not very good at the technology thing, but this is my favorite one. And so we got 2 over 15, and now we have to remember that we have to multiply that by 2 pi. So 2 over 15 times 2 pi is 4 pi over 15. You could put the 2 pi out front, but if you put the 2 pi out front, then it doesn't give you that option to turn it back into a fraction. So yeah, I just put the 2 out front and then I add the pi, so 4 pi over 15.
So using technology, we were able to determine that this was 4 pi over 15 units cubed. Now, you might be asking yourself, why? Why am I learning another method? I could have solved this equally as well using the washer method. And you're perfectly correct. You could do this using the washer method. And I mean, we could do that right now, but the difference between using the washer method and using the shell method is using the washer method, you have to set up 2 different integrals. You have to set up an integral for your outer radius and then your inner radius, and you have to subtract them. And so the shell method, we were able to do this using one formula. It was quick and easy, one set of integration. But you're right, if you wanted to use the washer method, you would get exactly the same answer. Okay, in this example, we are going to revolve the different direction. So find the solid of revolution formed by revolving the region, this region, bounded by x equals e to the negative y squared, and the y-axis. So it's bounded here and here, and we're only going from 0 to 1. That's important, from 0 to 1. About the x-axis. So we're revolving this direction. Now remember, whenever you are using the shell method, you want to make your rectangles parallel to the axis that you are rotating around. So I'm going to make my rectangle right here, and then that's what's going to go all the way around this axis. And so we need to figure out what is our radius, what is our height, and what is our width. Because remember, that's how you find the volume of a shell. So because we're cutting our rectangles this way, it's going to be dy. It's going to be our width here, dy. Our radius is going to be the distance from here to there, and we will call that y. That's the distance of y. It is changing depending on where you cut that rectangle, but it is always from here to here, which is some y value, right? And then the last piece of this would be the height, and the height of this is going to be from here to here, or if we were to cut a rectangle here to here, no matter what, the top of that rectangle is always falling on this curve. So our height, our h of x, or h of y, because we're doing dy, is this equation here. One nice thing about this is I don't have to rearrange this to be in terms of x, which trying to rearrange that to be in terms of x could prove to be a little bit of a nightmare. So that's really nice about this. So I have all the information that I need to put this into an integral. So remember, when we are trying to find the volume of a cylindrical shell, which really we are making shells this direction now, what we need is we need the height, we need the width of the shell, and we need the radius. If I have those three things, then I can find the volume of this, because the volume would be the surface area, which the surface area is 2 pi r, that's circumference, times the height. And then to get the volume, all we need to do is multiply it by the width. Because we're making an infinite number of these cylindrical shells to create this structure, which I didn't show the 3D image of this being revolved around, but the 3D image of this being revolved around, we're taking all these cylindrical shells and putting them inside of each other, kind of nesting them like those Russian nesting dolls. We are going to take the integral, and we are differentiating with respect to y because of dy, so from 0 to 1, we need to multiply our radius, which our radius is y, times our height, which is e to the negative y squared, times the width, which is dy, and then don't forget to multiply by 2 pi. Now, we could definitely integrate this by hand. To integrate this by hand, you'd have to do u substitution. You have kind of the equation here with that on the inside, and then when you take the derivative of that, you can start to see the derivative on the outside. So we could use u substitution and integrate this by hand, but we have technology, and so anytime we have a definite integral, I'd recommend using technology. If you are planning on taking the AP test, then I would pause this video and I would work this out by hand and then make sure you get the same answer. So anyone taking the AP test, you will need to do these by hand. But I mean, in this day and age, everybody has technology in their back pocket. So that's what I would do.
Okay, so in this example, we were trying to calculate the integral from, what was it? It was 0 to 1 of y times e to the power of negative y squared dy. And that is not going to give us a fraction again, so I'll go ahead and I will put that 2 pi out front, and we get 1.986 if we were to round it. So 1.986 would be the volume of that shape.
Using technology, we figured out that the volume is 1.986 units cubed. Now, again, you might be thinking, why? Why am I learning a new method? I spent so much time on discs and washers. So this one would have been just a really simple disc method. So why the heck am I making these shells? Well, if we were to do the disc method on this, I just want you to think about this for a minute. If we were to do the disc method on this, we would have this, and it would look something, let's see here, let's see if I can even draw this out. It's going to look something like that, kind of 3D. There is nothing hollowed out, and so you're right, you could cut there, and then just continue to make these cuts, right? And have all these different discs. Now, one thing that you need to know is that this is the axis right there. In order to do the disc method, you would be cutting this way. You would be cutting that way. You'd be making discs in that direction. And when you cut in that direction, everything is going to be in terms of x. To rewrite this equation in terms of x, you would need to do some serious algebra. I'm not saying that it's impossible, it's just a lot more work. Because not only do you have an e to the negative y squared, but you also have a y squared. And so then you're taking into consideration a square root symbol with logs. So it's just a little bit uglier, but you certainly could do this using discs if you want. And again, if you're wanting a challenge, go ahead and pause this video and work it out using discs and see if you get the same answer. You should. It's just a little bit more work. Okay, in this example, we are actually going to work this problem both using washers and then using shells so that you can see that you can use both methods anytime you would like, but maybe you'd prefer one over the other. So I'll let you choose which one you prefer. So in this example, we have find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, and x equals 1 about the y-axis. And so I've drawn that out here for you where this is x squared plus 1, this is x equals 1, and that's y equals 0, and because there are these points of intersection here, that is the region that's bounded. So that's the region that's bounded. That is what we're going to rotate around the y-axis, and when you do, you get a shape like this. Now, you might think this is a pretty straightforward washers, right? We're going to start with the washers method. Let's go ahead and write that down. Washer. So you might think that's pretty straightforward washer. The outside radius is going to be from here to here, which looking at this graph is always going to be 1. So my big R of x is 1. No big deal. My inside R of x is just going to be the equation, right? So my inside R of x is x squared plus 1. However, we have a problem here. One, we have to do everything in terms of y. But second, that inside radius isn't the inside radius the entire time. We actually have two different pieces of this. We can cut this graph here and find the radius of find the volume of the bottom portion of it, find the volume of this bottom portion, and then find the volume of the upper portion. And if you try to do it all in one go, using the inner and the outer radius, you're actually not going to get the right answer. You have to cut it this way and add them together. So again, because we're using the washer method this time, we are going to have to integrate with respect to y, meaning everything has to be in terms of y, because we're making our cuts this direction. We are cutting discs like this, which means this is dy. So this bottom portion shouldn't be that big of a deal to find the volume of it. It's going to be pi. We're going to integrate from 0 to 1 of just 1 squared dy. Dy. So that part's not that big of a deal. And then we have to do the washer method there. So plus pi, now we're going to integrate from 1 to 2, 1 to 2. And we have to put this in terms of y. So when we put that in terms of y, r of y is, well, we're going to subtract 1, and then we're going to take the square root. So here's our inner radius. This is still our outer radius. So we'd have 1 squared minus the square root of y minus 1 squared dy. And now we can plug that into our technology and get what that actually equals. Of course, we could integrate that by hand. That wouldn't be that big of a deal, but let's plug it into our technology.
Okay, so in this particular example, we had two different integrals that we were adding. We were adding the one that was from 0 to 1 of 1, and I think it was in terms of y, plus we were adding the integral from 1 to 2 of 1 squared minus the square root. Well, I can't reach the square root because there's a bar down here. I don't know how to move it. Okay, so the square root of, what was it? Y minus 1 squared, and so that cancels out. And then this, gotta put some more parentheses around there. I'll get good at technology eventually, guys. dy. Why are you unhappy? Why is it unhappy, guys? What did I do wrong? Well, we know that that's just a 1 dy. Maybe I can't add them together in the same. That doesn't seem right, but let's see. Let's go down here. So we know that that is 1. That's going to be 1 to 2 of 1 minus y minus 1 dy 0.5. I don't know why it didn't let me do them together. I must have added something wrong. So 1.5, and then remember you've got the pi on there because there's a pi on the outside of both of them. So you've got 1 pi plus 0.5 pi, which is 1.5 pi, and 1.5 is the same thing as 3 over 2. So 3 pi over 2 would be the volume if we were to add those two segments together. So 3 pi over 2 is our volume there.
And plugging this in, we got 3 pi over 2. Let's try this again, but let's use the shell method. And let's compare and contrast them. Let's see which one do we like better in this particular case. And that's not to say that we'll like it better every case, but let's see which one we like better in this case. Okay, so using the shell method, we are going to make our rectangles parallel to the axis of rotation. So parallel to the axis of rotation, our rectangles are going to look like that. And so then we're going to swing that rectangle around, and we are going to make cylindrical shells that are going to fall within this. And that's how we're going to find our volume. So we need to know what is our height, what is our radius, and then what is the width. And because we're making our cuts this direction, we're going to say this is in terms of dx. Our height is going to be that function, so we're going to say h of x is x squared plus 1. We're going to say our radius is x, and then our width is dx. So we need to multiply or do our integration. So we have 2 pi, and we are integrating with respect to x, so 0 to 1. And we're going to do our radius times our height times our width. And of course we could integrate this by hand, and maybe some of these I should do by hand just so you can see them. If you are planning on taking the AP test, make sure you practice integrating some of these by hand. But because we have technology, we can do that as well. Let's integrate this one by hand, just for fun, just for good practice. So if we integrate this by hand, we have to multiply that in. So we have 2 pi, 0 to 1 is going to be x cubed plus x dx. To integrate, we increase by a power, and we divide by that new power. And so we have 2 pi times 1/4 x to the 4th plus 1/2 x squared. And we need to plug in 0 and 1. You always plug in the upper bound first. And so when we plug in our upper bound, we're going to get 2 pi times 1/4 plus 1/2. And then we'll get minus 0. Because when you plug in 0, it's still 0. So 1/4 plus 1/2, well, this is the same thing as 2/4, which means that we have 2 pi times 3/4, which means that we have 6 pi over 4, which is 3 pi over 2. Same thing. Same thing. So we're going to get the same thing either way. whether you use washers or whether you use shells. The thing about the washer method was that we did need to break it into those two pieces, and in the shell method we did not need to do that. I'm not saying that that makes the shell method better, but in this case I would prefer to use the shell method. It was less work, took us the equal amount of time when we even integrated this by hand. And so this is one where I would do the shell method over the washer method.